Hey everyone, welcome back. In our last video we talked about calculating moment of inertia for an object, which is, as I've been calling it, the angular mass of an object. How we're going to treat the mass, how it's distributed dependent on its shape. And the reason we started off talking about that is because as we try to figure out the angular acceleration of an object, we need to know its moment of inertia, and we're going to need to be able to come up with a representation of torque, and that's going to be the goal of this video, is looking at torque so we could solve for angular acceleration given a certain scenario. So let's start off. We're going to look at two examples to demonstrate everything that we need to consider when calculating torque before I just give us an equation. So let's consider two doors. These doors are identical, where this is a top view looking down. So this is our hinge, and then this is our door sticking out, and this is supposed to be a door handle. I'm not sure why I drew one on only one side, but that's our door. So what we're going to consider is, in this segment, we're going to consider applying a force to this door at two different distances from the pivot. So you can see this door on the left, we have a radius, the distance from our pivot point, and where we're applying a force of R1. And then force 2 on our second door over here is being applied at a distance R2. And so what we're going to be interested in is if this door moves an angle of theta. So we got a change of angle theta 1 and a change of angle theta 2. And so if we let R2, our radius of our second door, be equal to 2 times the radius of door 1, we could represent these, instead of having the subscript, we could just say that the radius of door 1 is R, and then of course the radius of door 2 is going to be 2R. And so we're interested in, what we're going to look at is moving the door over the same change of angle. Both doors are going to open up the same amount. So we could think of it as pi over 2, 90 degrees, we're opening the door, or whatever angle. We're going to end up canceling it anyway, so it won't matter, but we could represent both of these angles, change of theta, angle 1 and 2. We're just going to represent that as theta. And then, so if we think back to our work formula, we got a force over a distance, right? So in each case, we have this force being applied to the door, and then we're opening it, and it's going to open the same distance, right? We're going to have the same change in angle. So that means if we're thinking about a point out here on the door, this distance it's going to travel is going to be the same for both of those, which means the work, the net force, or the total work going into both of these doors should be the same, because we have conservation of energy. So we could compare these two by saying that our work 1 is equal to our force 1 multiplied the dot product of S1, and S1 is just going to be the arc length, the distance we push that door over. And so we could think of the same thing for door 2, where work 2 equals our force 2 times our arc length 2, S2. So replacing our arc length, we know that arc length is equal to our radius times our angle. So all we're doing is multiplying by our R1 in this case by theta, and then R2 by theta. And using these relationships that we've defined before we started down this path, we could replace our R1 subscript 1 and theta 1 with R theta. And for our second door, we could replace R2 with 2R, because keep in mind it's 2 times the radius of 1, and then theta is going to be the same for both of these. And since we know that our energy is going to be conserved, we're opening this door, we're moving it the same distance in both scenarios, we're just applying a force in different each spot. We could set work 1 equal to work 2. And plugging in what work 1 is and what work 2 is in this equation, we see that F1 R theta equals 2 F2 R theta. And if we simplify that, we could get rid of like terms, or get rid of our radius and our theta, because we have one on each side of our component. We end up with a force 1 equals force 2, which should make sense because we went over for the force 2, we traveled twice the distance, so we have to have the force that's being applied in half for conservation of energy. So we have the same amount of work. So torque, because so what we'll see here is that torque is dependent on the location that we're applying a force at R, either in this case R1 and 2, and it's dependent on how much the force being applied, the magnitude of force being applied. So look, from this, looking at this example, we should take away that it depends where we put our force and the magnitude of force. But there's another idea we need to think about as well. In this case, as you could tell how I have it drawn, is that the force is perpendicular to the door, 90 degrees. So let's take an example, or look at an example that this isn't the case. So here we have 3 doors, the same doors we were working before. Well, it's drawn a little different, but same idea. We have a hinge and a door, and we're going to be applying forces. And this time, instead of varying the position R that we're applying the force, we're going to vary the angle of the force being applied to the door. So looking at these 3 scenarios, generally when you open a door, you're pushing on it at 90 degrees. And we know that the door is going to open. And then we could apply an angle here. I just chose a angle between 0 and 90, so 45. And we'll look at that, what the results of that are. And then we could also apply a force either going 180 degrees, the opposite direction, anti-parallel to the radius, or we could apply a force pulling outwards of at 0 degrees, so parallel to the radius of the door. And in this scenario, it should be obvious that the door is not going to move, right? If you're pushing the door into its hinges, you're not pushing in the direction you want the door to rotate, so we can assume that this door isn't going to move. So looking at each of these, we know that our angular acceleration for this first one's not going to be 0, therefore our torque can't be equal to 0, and the same thing for the second door. But our third door, our angular acceleration is 0 and our torque is 0 as well. So what we should be able to take away from this is that our angular acceleration, if we're starting at some value, or we have some value 90 for 90 degrees, and at 0 degrees we have no angular acceleration, there must be some dependency on the angle that we apply our force. So if we look at the perpendicular force, that's what this little upside down T stands for, if you're unaware, we could represent it as F sine of theta, which of course the sine of 90 degrees is 1, so we just get a force F. But if we look at the second situation where we represent it with theta, here we have a angle of 45. We also have an angle of 135. It doesn't matter which one you choose because the sine of 45 and 135, either of these angles is going to be the same. And so we know that we get some perpendicular force on this door equal to F sine of 45. And the third one, we have an angle of 180 or 0. So if we plug that in, we're going to have a perpendicular force of 0. So what we should take away from this is in the first segment we saw is that our torque is going to be dependent on our magnitude of force as well as our position. And in this one, we're starting to see that we have a dependency of the angle we push on the door and the magnitude of force. So what we can conclude is that the magnitude of torque is going to be equal to the magnitude of force times the magnitude of our radius times the sine of theta. Or, if you remember, that is also the representation of our cross product. So torque actually comes out to equal tau equals the force vector crossed with the radius vector, or the position vector. And so what the cross product gives us is a vector that is perpendicular to both, or orthogonal to both force and radius. So if our force and our radius are in the xy plane, we know that our torque will be pointing in the z direction. And if we look back at the right hand rule, there's a simple way to come up with whether our direction is going to be positive or negative. So generally we're going to be working in the xy plane if we have the choice to choose where what coordinate system we're working with and which plane we're working in. We are going to work a problem that we don't have that luxury, but it isn't any more difficult, I don't think. But our right hand rule shows us that if we curl our fingers in the direction of our applied force, our torque, and curl them around, that our thumb will point into the direction of the torque. And so you can see here in this illustration that our thumb is normal to the surface that's rotating. It's orthogonal to that surface, is what we should expect. Okay, so let's look at a problem that we can, it's a simple problem that it will be a good review of the cross product as well as giving you an idea of how to solve for torque. So find the torque on a rod that has a force being applied at r equals 1 meter in the x hat direction, 2 meters in the y direction, and 3 meters in the z direction. If our force is 10 newtons in the y direction and 20 newtons in the z direction. So remember, our torque is just equal to our force crossed with our radius, which we could represent here. And we will take the cross product. If you don't remember how to take the cross product, you could pause the video here and use this to help you. Which should give us something like this. And remember, the cross product does give us a vector answer. So unlike the dot product where we sum these after multiplying, we're going to leave it in XYZ components, which turns out to be negative 10 newtons meters in the x hat direction, 20 newton meters in the y hat direction, and minus 10 newton meters in the z hat direction. So one thing you might notice if you've been paying attention to your units is that your units of torque is newtons times meters. And we write it like this so we don't get confused, because if you remember what the units of work is, it's a force over a distance. So it's newtons times a distance. But when we talk about work, we represent our units as joules. And torque, we generally write as newtons times meters to avoid confusion when we're talking about both of those. All right, so let's look at another problem. Here I've attempted to draw a seesaw. If you're unaware, this is what it's supposed to look like. So basically we have a pivot point here, some board as our platform, and what's going on here is we have a force being applied straight downwards, and we have on the other side this rope that's holding the seesaw back from coming all the way down and touching the ground on this side. And this seesaw is a little different because we're going to give it different lengths. On the left side of the seesaw, we're going to have it 3 meters, and on the right side it will be 2 meters, just to make the problem a little more interesting. And so if we want to figure out what the tension in this rope is, we could just solve our sum of torques equals our moment of inertia times our angular acceleration. And so that should have a vector. So because our seesaw here is being held back by a rope, we have a force on this side, we know that the angular acceleration is going to be 0. So our torque being applied to the left side must be equal to our torque being applied to the right side, just opposite direction. So we could say the sum of torques equals 0. So we could say torque 1 equals the opposite of torque 2. And so our torque 1, we have this force 1 being pushed down on this side. It's being applied at an angle. Remember that torque not only depends on how far out we're pushing our radius, but also at the angle. And we're shown here that our angle with respect to the ground is 20, which would make this 70 degrees, the angle that we're interested in. So don't get screwed up. When you're given the wrong angle, we should be able to calculate this because this is parallel to the ground and this force is supposed to be perpendicular. So where are we at? And then on our right side, we have our tension, which I'm representing as our force 2, what we're solving for, and then we're out at radius 2 sine of theta 2. So solving for tension, we end up with this ratio. And we could plug in all of our values. So the rope, sine of theta 2, as you see down here, I put in this 90 degrees because this little box here is showing us that it's a right angle. And then, of course, our rope is tied off at 2 meters from our pivot point, and our force 1 is being applied 3 meters from our pivot point. So plugging all this in, we find that our tension in the rope is 211 newtons. Okay, let's look at one more torque problem. So it's kind of hard to tell what I have drawn here, but it's supposed to be something like this, a wheel. It's got a rim that we could think of as a hoop, and it's got two sets of spokes, to what we're going to think of as rods when we try to solve for the moment of inertia. So we have this wheel, we got our 2 rods that are making this reel. We're told that each rod is 2 meters in length and weighs 7 kilograms. And then we have this hoop that we're told weighs 10 kilograms. And then of course we know the radius of this hoop is going to be half of the length of these rods. And we're told that we have an angular acceleration of 3 radians per second, and that should be squared. Radians a second squared. And we want to know what our torque is. So what we haven't really talked about yet is the fact that we've talked about that the magnitude of torque equals our moment of inertia times the magnitude of acceleration. But what we haven't mentioned is that when we talk about moment of inertia, when we did the video and we integrated over the material, the mass volume of the material in our previous video, we came up with that our formula sheet. We found out that our solid cylinder equals 1/2 mr squared. But what you should think about when we have integration and when we integrate over something, if we have discrete values like we have here, we have a rod, and a hoop, instead of integrating over this shape to find it out, we could just take each component and sum them together. So here, looking at the moment of inertia table once again, you could see that letter A, our I equals 1/12 ml squared, is a good representation when comparing to our the rod for this wheel, 1/12 mr or ml squared, the entire length of it squared. So, and we have 2 of those. So here I have it represented 2 times the moment of inertia of the rods, because we have 2 rods, plus the moment of inertia of a hoop. So let's go back and look at what the moment of inertia of a hoop is. which is just mr squared, letter G. So we're going to have two letter A's plus a letter G. So when we plug in the values for those, we got 2 times 1/12 m mass of the rod, length squared, plus mass of the hoop times, and I wrote it as the length divided by 2 to get the radius, and then just squared it. So simplifying somewhat, just distributed the 2 and pulled out our fraction. Simplified a little more, just pulled out the L squared, and we're left with L squared alpha and 1/6 the mass of the rod plus 1/4 the mass of the hoop. These are all values that we were given initially, so since this is equal to the magnitude of torque, we should be able to just plug in our known values. 2 meters squared times 3 radians a second squared, multiplied by 1/6, 7 kilograms, plus 1/4, 10 kilograms. And this gives us a magnitude of torque of 44 newtons. So just remember, whenever we have a situation where we have multiple shapes that we could just look at our table. Once again, I'm going to only give us shapes that are off this table. But when we have different shapes combined, all we need to do is sum the moment of inertia for each shape. So here we had 2 rods and a hoop, and we just added those together. So looking back at our comparison of translational and rotational motion, we've made it down on the right side, 1, 2, 3, 4, 5, down to torque. And so what we have left to talk about is our angular momentum and our rotational kinetic energy. So that will be what we cover on the next video, and then I'll probably have a follow-up video that will work some random problems just to give some more depth to these ideas. Let me know if you guys got any questions. That's it for this video. Have a good day.